Hello guys, today we're gonna see about the math behind neural networks or perceptron. Basically, perceptron is a mathematical model that that takes input and in that model and gives out an output. We can call it as y hat. And if we train this model, for example, the if we want to find out a function, this function, for example, if we want to graph this function, this model will give us the graph 1, 2, 3, 4, 1, 2, 3, 4, 4, 1, 2, and 2, 4, etc. The the work of this perceptron is to estimate the function. The estimation of function. Let's see how it estimates the function. First, we need input and output pairs. We need input and output pairs 1, 2, 3, 4, and 5. And the output will be 2, 4, 6, 8, 10. This input and output pairs will be fed into the network and it will find out the relation relation between x and y. F of x equal to 2x. It will find out this relationship between the function. Let's see how it works. And the underlying structure of the perceptron looks like this. The perceptron looks like this. It has weights, and it will be multiplied with the input, and we will add a bias. The why we add bias is if we have like this, if a function predicts out like this, if we add the bias, it will turn it like this. It will change the length this way. So we add the bias. So let's see. It will looks like this, and when we give an input, yes, let's take an input from this x equal to 1, y equal to 2, and you give an initial random weight of 1 and a bias of 0. In the computers, the weights are randomly initialized. If we give this and the bias 0, maybe in the first try the model will land on this, we don't know until we train the model. So we give the initial bias as 0, and let's let's see what happens when we train the model. And if we give the forward pass forward pass, the prediction will be the weight plus multiplied by the input plus the bias. That will be 1 plus 0, and that will be 1. If we and the output we want to have is 2, and if 2 is the output we needed, the way we get this 1 to 2 is by changing the and weights and biases by by random to certain values, and when we give the input, it will correctly predicts the output. Basically, the neural networks or the perceptron is the function estimators. Let's see how it works. We calculate the loss, or loss L equal to, we calculate it by y minus y hat whole square. The reason we are squaring it, because we don't want any negative values. That's why. And in order to change the weights and biases, we need to update the weights and biases with this loss value. And the how we do is taking the gradient of the loss with respect to the weight, and the gradient of the loss with respect to the bias, and we will add the new will add this the new weight will be the old weight plus the learning rate, because if we have a graph like this, we have a gradient in here, and we uh, want to be here. If we directly add this change this weight value by adding the predict we change this value little by little so that it gets here and not overshoots over here. That's why we are taking the learning rate, and usually take the learning rate as a small value as 0.01 as such, and we add the we add the loss we add the gradient we have calculated here, that is del L by del W. Let's calculate the first. First, we have set on the inputs and outputs, and we have set on the weights and biases over here as 1, and the output will be 2, and the random weight we have set over here is 1, and the bias over here is 0, and we take this values over here. The weight is 1 and the bias is 0. Let's calculate the losses. The loss of this will be del L by y hat, and del y hat by del of the weight, because due to the chain rule we first calculate the loss, and we take the gradient over the predicted output, and we take it back to the weights. That's why we are using the chain rule from the losses to the weights. Let's continue over here. The losses we have calculated the losses will be calculated by means we are not doing it now. Let's calculate the loss. The loss is, we are not calculating the loss, we are calculating the derivative of the loss with respect to the weights, and the loss we are taking will be minus y hat, y minus y hat whole square, and the derivative will be the derivative will be with y hat, derivative of y minus y hat whole square with respect to y hat. The derivative will be y hat times minus 1. The del L by del y hat. This is the loss we calculated. The the gradient of the loss we calculated with respect to the predicted output, and we should calculate this part. we should calculate the derivative with respect to the weights. This is wx plus b, derivative of wx plus b with respect to w. This gives us only x. Finally, if we take del L by del W, we have y minus y hat minus 1 times x. On the forward pass, we have gotten the value of 1 and we substitute it over here. Y we have 2 and in forward pass we gotten the value of 1 and minus 1 here, and the value of x is 1. 2 minus 1 minus 1. We got a value of minus 1. Let's calculate the value with respect to calculate the calculate the gradients with respect to the bias. For that, we have this, that is integral del y and del y hat with respect to del v, and the gradient with respect to y hat is, we have already found out that is this value, and the value is minus 1. The del y with respect to y is L. The del y is, there is del y. The del y we have gotten from the network. The del y is wx plus b, and we have to take out the derivative of this, and we will get after the video has cut off. I don't know why. Let's continue where we have left off. In this, we have calculated the derivative with respect to the bias, derivative of the loss with respect to the bias, and first we have to calculate the derivative of loss with respect to the output of the network and the derivative of the bias with respect to the bias, derivative of the output with respect to the bias. We have already calculated the derivative of the loss with respect to the output of the network, and that value gives us this, that gives us -1, and that is why we have given here -1. And with the with the output is given by the weight multiplied by the input and adding the bias, and we have to take the derivative out of this, and it gives us 1. The derivative of the loss with respect to the bias is -1, and now we have both derivative with respect to weights and the biases. We can now calculate the new weights and biases. We have to subtract the new weights multiplied by the learning rate, that is 0.01. We have written elsewhere, here elsewhere, I don't know where I put it. Here we have set the learning rate to be 0.01, and the derivative of the loss with respect to the derivative of the weight, sorry, with respect to weight. And we have already calculated this value. The old weight is 1, as we have set in this, and the new the learning rate will be 0.01, and we have calculated the we have calculated the the calculated the gradient with respect to the weights, that is -1 here, -1. And if we add this, we will get 0.01, and we can add this up, 1.01. This is taking us closer to the value of 2, and the new bias, and this is not taking us any closer to 2. Sorry, the new bias will be the old bias minus the learning rate and the gradient of loss with respect to the bias, and that we have calculated as here. The old bias is 0 and the learning rate is 0.01 times the gradient -1, and it will be 0.01, and we have updated the network, and the next output will looks like wx plus b, and it will looks new and new. It will gives us the answer of 1.01 times 1 plus 0.01. It will gives us 1.01 plus 0.0, something like that, 1.02, like that. It is approaching 2, and we have to do this step multiple times until we get the value 2. I'm just simplified the network with only one weight and bias gives y hat. I'm done the simplified method, but real neural network will have something like thousands of hidden layers, not layers, thousands of these neurons are like this, and the output will be according to your desired output. We have to do it recursively until the first value we have gotten, that is 1, and we have added weights and biases to it to change it to 2. And we have done it through the back propagation method. We have iteratively changed these weights and biases, so that if we add these weights and biases to the network, it will convert this input into this output, and the internal representation is applied into this perceptron or something like this.